Hey everyone, welcome back to Calculus 3. This is going to be lecture 8 of the course. In this section, we are going to begin to explore the mechanics of differentiation and integration of vector-valued functions. Okay, and so let's jump into it. And so what we'll start with is a definition of differentiation for vector-valued functions. So we'll naturally start with derivatives, just like we did with real-valued functions. So let's define this. The derivative of a vector-valued function R is defined by, how do we define it? Well, very similar to what we did with real valued functions. We'll say that the derivative of R is equal to the limit as delta t goes to 0 of the function R evaluated at t plus delta t minus the value of the function at t, all divided by delta t. All right, so the derivative of this is defined by this guy here, and we say that that's true for all t for which the limit exists. Okay, right, so there's the derivative. Now that's should be very familiar, right? If you took Calculus 1, which you probably did, if you're taking Calc 3, you've seen this. Just swap out the R for F, real valued F, and you have the same thing. So it's all really the same mechanics. And we'll see kind of how this works in a moment, but it should look very familiar at the onset, hopefully. Right now, just like with real valued functions, we use the term differentiable at a point and differentiable on an interval. And what does it mean? Well, it just means that the derivative exists. If the derivative exists at a point C, we say it's differentiable at that point. All right, so let me write that. If R prime of C exists, we say R is differentiable at the point C. Right, and then of course we can say that R is differentiable on a particular interval if all of the points in the interval are differentiable. Okay, so if R is differentiable at all points in an interval, we say it's differentiable on the interval. Okay, now similar to the real valued functions, there are a number of ways to notate this. One of the ways that becomes more common with vector valued function is using this notation. All right, so kind of a big D with a little t subscript. But you also have the familiar d dt of R of t, and then also the also familiar dr of dt. Okay, so those three notations are common. They all happen a lot, actually. With differentiation, the notation can vary quite a bit depending on who's doing it and the circumstances. The nice thing about this, about vector valued functions and derivatives, is that the differentiation can be done, which we'll see in a moment, on a component by component basis. Okay, so differentiation of vector valued functions can be done on a component by component basis. Right, so what that means is to differentiate the entire vector valued function, you can differentiate the individual components. All right, so let's take a closer look at that. Let's apply the definition and see how that works. Okay, so if I start with r prime of t, right, that's the vector valued function r, and I want to differentiate that. Just applying the definition, we know that that is going to be equal to the limit as delta t goes to 0 of r of t plus delta t minus r of t, all divided by delta t, right? So that's just the definition, right? Now, and so you should hopefully remember what this notation describes, right? You've got r evaluated at t plus a little bit, right? So some distance from t, and you're going to subtract off r evaluated, strictly speaking, at t, and you want to divide that down. Now, as delta t gets closer and closer to 0, these points, they shrink down to being basically neighbors of one another, and you get the derivative. Right, so but let's see how this works. Let's just expand this given that r is a vector valued function and see what this looks like. Right, and so we'll just assume r is a two-dimensional vector. And so we get the limit as delta t goes to 0 of, now in the numerator you're going to have basically an f of, so we'll write it, f of t plus delta t, and that's going to be the I component, plus g of t plus delta t, and that's the j component, right? So that's just expanding this into the two components. Remember, this is assumed to be a two-dimensional vector, right? The same thing applies to three-dimensional vectors. It just gets a little lengthy. Okay, and then we're going to subtract off r of t, right? So there, that would be like subtracting f of t times I, and also subtracting g of t times the j component, right? And then the whole thing divided by delta t. All right. And now we can do a little rearranging here, can't we? Basically, we can take this piece here and put it next to this piece over here. The f's by the f's, the g's by the g's, right? And so if I do that, I get the following: f of t plus delta t I. I'm going to actually pull them both together and we'll factor out the I. So we're going to put this guy and this guy together and factor out the I. Right, so we can do that. And then you get the I right there, and then plus, and then let's put the g's together. Factor out the j, and then the whole thing is over delta t. Right, and you can imagine what comes next, right? We're just going to split the thing into two and take the limit separately, right? So the limit as delta t goes to 0 of f of t plus delta t minus f of t all over delta t. Okay, and we'll just say that whole thing is the I, and then plus the limit as delta t goes to 0 of the other piece, and that's the j. Okay. And so what is this? Well, this is just f prime of t times the I vector. And what is this? That's just g prime of t times the j vector. There we go. Right, and so that's what we mean by component differentiation. Right, so you start by wanting to differentiate the entire vector, and to do that you differentiate the first component, and then you differentiate the second component, and voila. Okay, so this is basically the proof of the following theorem, right, which we'll state kind of quickly since it's already been said, but just for completeness sake, if r of t is equal to f of t times the I vector plus g of t times the j vector plus h of t times the k vector, so a three-dimensional vector or a two-dimensional vector, then the derivative of r is equal to the derivative of the components, f prime of t times I plus g prime of t times j plus h prime of t times k. And that's basically what we just said. Did it for two-dimensional vectors, but you can imagine how the proof would extend naturally into the third dimension just by adding that k component. It's all the same argument, though. Okay, so this is very nice. Good news, basically, right? Most of the work we did when we were learning about derivatives of real valued functions will carry over automatically to vector valued functions, right? So most of the work we have done already will carry over naturally to vector valued functions. Thank goodness for that, right? Because we had all of Calc 1, which is basically derivatives. Now all of that stuff carries over nicely into vector valued functions in Calc 3. There are some subtle changes which we will address. There are some subtle differences, but most of the way we were calculating those derivatives translates directly, since it's just, differentiating a vector valued function. It basically boils down to differentiating two or more real valued functions and just kind of keeping track of the structure. Let's do an example. Let's take a look at an example here. Let's differentiate. Let's find the derivative of RT equals t squared I minus 4j. Okay, so ddt of r of t is going to be equal to ddt of this guy, so t squared times I minus 4j, right, which is really just, and I'm taking way more steps than you would normally have to do with this, but I just want to make sure it's clear how we can think about this. It's really the derivative of the first component minus the derivative of the second component, right? And so the derivative here is 2t times I. And then what's this? Well, it's just 0. The derivative of 4, the derivative of that constant is 0, so this would be just minus 0. And so the answer here would be 2t times the I vector. That's the derivative of this particular vector valued function. Let's take a slightly harder one here. Let's say instead that RT is equal to 1 over t times I plus the natural log of t times j plus e to the 2t times k. Right? So these should look like old friends, right? If you recall calculus 1, 1 over t, derivative of that, derivative of natural log of t. These are old friends. We've seen these before. All right, so the derivative here is again just the derivative of the components, right? But you got to keep track of the structure of the vector valued function, right? So remember, you're differentiating the components and kind of keeping everything in place. Right? So just real simple if you're comfortable with vectors, with the idea of a vector. And if you're comfortable with this kind of derivatives, right? So this one, remember, this is t to the negative 1 power, so that derivative is just negative 1 over t squared. And then the derivative of natural log of t, everybody should remember, that's 1 over t. And then this guy is the chain rule, right? So you'll have to do a 2e to the 2t. Okay, so that's the derivative here. Very nice. Okay. All right. Let's try something a little different here. Let's do another example. This time, let's define a couple of vectors, and then we'll pull in some cross-product talk and see what we can see here. So let's say we want to let r of t equal cos t times I plus sine t times j plus 2t times k. Okay, that's r. And so then let's go ahead and let's try to find All right, a couple of things. So first of all, we want to look at r prime of t. Okay, so we need that one, and then let's try to find r double prime of t, so the second derivative of r, right? So higher derivative, higher order derivative, second derivative. Let's differentiate r and find the second derivative. That's those two, and then let's take the dot product and see what happens. So let's do r prime of t and dot it against r double prime of t. And then while we're at it, let's do the cross product of the two. Getting a little crazy there. R prime of t cross r double prime of t. Okay, so we'll do all four of those. Okay, so this will be 1, 2, 3, and 4. Let's try to calculate each of these things here. All right, so number 1 is r prime of t. Well, that's pretty straightforward, right? You've got cos, sine, and 2t. They don't get much easier than that. So the cosine is negative sine. And then the derivative of sine is cosine. And then the derivative of 2t is just 2. Okay, all right, so there's that one. What about the second derivative? Well, the second derivative is just the derivative of the first derivative, right? So we're going to differentiate this one instead. Okay, and so when we do that, we have negative sine t, the derivative is negative cos t. And the derivative of cosine of t should be negative sine of t. And the derivative of 2 is just 0, so this would be technically 0 times k. And so you could write this as negative cos t times I minus sine t times j. Okay, so you got that one. First one was this one, and now you have that one. Now what about the third item? Let's calculate the dot product here of these two. So we're looking for r prime of t dotted with r double prime of t. So the dot products. And when I do the dot product, I just kind of like to write it differently just so I can keep track of the components. So this would be negative sine of t, cosine of t, and 2 dotted against negative cos t, negative sine t, and 0. Okay, so that's what that is. And so we can easily calculate this. It'll be negative sine times negative cosine, so that's just going to be sine times cosine. Plus, and then it's cosine times negative sine. All right, so that'll be plus negative sine t cos t. And then plus, that's just the 0, right? So what do we get? Well, in this case, we get sine cos minus sine cos plus 0, right? So you get 0. So the dot product in this case is 0. I wouldn't assume that that's generally true. It just happens to be true here. It has to do, obviously, with the fact that those sine and cosine signs flip on us, don't they? And what about the cross product? What does the cross product look like? Okay, so we're again trying to do the cross product of the first and second derivative of a function. Well, let's see. So we have r prime of t crossed with r double prime of t. Well, let's just take care and write everything out here. So this is negative sine of t, cos t, and 2. And then negative cos t, sine t, that's negative, and 0, right? And then we need to do the cross product, which is like doing the okay, and so let's write it out. Let's be real explicit. So remember, we get cross out the first one, and you get this sort of sub-matrix here. So it'd be cos t 2 negative sine t 0, and that's the I component, times the I vector here. And then minus, and you cross out the middle one, and it's negative sine t 2 negative cos t 0 times the j component. And then finally cross out the third column, and you get negative sine t, cos t, negative cos t, negative sine t, times the k component. All right? And so just be careful when you're doing these, because it's kind of a little bit of bookkeeping here, right? So you've got, what do you got? 0 minus negative 2 sine t times I, and then minus, and then this is again 0 minus negative 2 cos t, okay, times the j vector, and then plus, now here's where you get negative sine t times negative sine t, so that's sine squared t, minus, and then it's negative cos t times cos t, right? So be careful here, times the k vector. And so let's clean this up a little bit. So I get, what do I get? 2 sine t times I, and then it's minus 2 cos t times j, and then what do I have here? Plus, it'll be sine squared t, and then this is going to be plus cos squared t, isn't it? Nice. Okay, and so the whole thing cleans up a little bit more. So we have 2 sine t I minus 2 cos t j, and then this is just 1, so plus k. All right, so that's the cross product of the first and second derivative. All right, very good. Okay, so many of the, as you could probably guess at this point, many of the properties of real valued derivatives have counterparts for vector valued functions. And so that's what the next theorem is all about. All right, so the next theorem is a little bit of a laundry list type of theorem, but it has a lot of information in it, and it's really depending on, I mean, it's really kind of bringing forward a lot of the overlap between real valued derivatives and vector valued derivatives. So we'll let R and U be differentiable vector valued functions of t. Differentiable vector valued functions of t. Okay. And we'll let f be a differentiable real valued function of t. Okay, so you got some vector valued functions and you got some real valued function here with f. And we'll let c be a real number, i.e. a scalar. Then, all right, now off we go, right? So we've got two vector valued functions, a real valued function f and a scalar c. So we'll just kind of go through this. So the derivative of, with respect to t, of a constant times a vector valued function is just equal to the constant times the derivative of the vector valued function. Right? So real natural there. Totally perfectly mirrors what you'd expect to see for real numbers or for real valued functions. Okay. The second one is the derivative of a sum of vector valued functions. So if I have r prime of t plus or minus u, r of t plus or minus u of t, they're not derivatives yet, they're differentiating that sum or difference, then it's just going to be the derivative of r plus or minus the derivative of u. Right, just exactly like you'd expect, exactly what you get from a normal real valued function like what we're used to. Now, the next three are kind of interesting. They all three include products, and they're basically three different versions of the product rule. So the first one is if I have a real valued function f and I multiply it times a vector valued function r, and I want to take the derivative of that product. Right, now remember, at t, f is basically a scalar, isn't it? Right? Okay, so this makes sense for particular values of t. Right, now what happens when I want to calculate the derivative of this? Well, it's the product rule, actually. It's f of t times r prime of t plus f prime of t times r of t. Okay, so this is just exactly like the chain rule. So first times the derivative of the second plus the derivative of the first times the second. Exactly like the, not the chain rule, the product rule. So these are product rules. Right, this one and then the ones to follow. So number 4. So remember with vectors we had the scalar product. We had the scalar multiplication, which is kind of like what this is. Right. We also had the dot product, and we had the cross product. Right. So the second one deals with the dot product. So if I have r of t dotted with u of t, and I want to take the derivative of that, then it's actually going to be the product rule again. So you get r of t times u prime of t. Remember, these become scalars, right? Plus r prime of t times u of t. Right? So again, it's the first times the derivative of the second plus the derivative of the first times the second. Right? So that's the product rule again. And then number 5 is basically the product rule for the cross product. These are all 3 different kinds of products you can get with vectors, and here again you get r of t cross u prime of t plus r prime of t cross u of t. Right, so just like the previous 3. Right? So it's all the same pattern. It's just here you're doing real valued function times a vector valued function. Here you're dotting 2 vector valued functions, and here you're crossing 2 vector valued functions. But all 3 of them are they just use the product rule. Okay, and so then there's another item here. Number 6 is the derivative of a vector valued function evaluated at f of t. Right, so f is a real valued function, so you've got a real valued function plugged in as the argument of this vector valued function. Instead of t, you've got f of t. And what's the derivative of that? Well, this is a version of the chain rule. So it's r prime of f of t times f prime of t. Right, so the outside function would obviously be r, the inside function is f, so you differentiate the outside first and multiply that times the derivative of the inside. Okay. And finally, last but not least, if r of t dotted with r, this one's a little different, if r of t dotted with itself is a constant, then that means r of t dotted with its derivative, its first derivative, would be equal to 0. Okay, so that one's a little different, but let's talk through. Well, we won't go through all of these. We'll use some of them in examples, but let's actually prove one of these just because it's instructive. So I think a lot of the proofs here are straightforward, and you could prove them using a lot of the vector techniques that we've already discussed. But let's look at number 4 in particular, just to see how these kind of work. So remember, number 4 is basically the product rule, but for dot product. Okay, so it's the product rule for dot product. Okay, so what we're trying to show here is that if you take the derivative of the dot product of 2 vector valued functions, then it's like the product rule that we're used to. Okay, so let's do this. Let's we'll let r of t equal, and I'm going to write it in component form just so we can keep track of this easier. Okay, so actually I'll call them F1 and G1, we'll say. So we'll let R be F1 and G1, and U of t will let be F2 of t, G2 of t. Okay, so so these are the two functions that we're going to dot together and take the derivative of. Okay, so then d of t of the dot product of these two, right? That derivative, well, let's write it out using in component form. So that's going to be d dt of, now remember what we're taking the dot product here, so it's going to be f1 times f2, right? Plus g1 of t times g2 of t, right? That's just the dot product definition, right? But we're taking the derivative. These are functions now, right? And so each of these has the product rule built into when we do the derivative, right? So we'll write it as, let's say, f1 of t times f2 prime of t plus f1 prime of t times f2 of t, right? So that's this one. And then we have to do the same thing over here, right? So remember, we're just using the product rule on these normal real-valued functions here. And so the second one would be basically the same thing, g1 of t times g prime of 2t, g prime 2 of t, plus g1 prime of t times g2 of t, right? And that's this one. Right, so you see how the product rule just kind of comes out of this, because ultimately the differentiation takes place at the component level, right? And so we can then regroup things, right? So in particular here, I want to regroup this guy here with this guy here, and then I want to put those together, and then I want to put those two together. Okay, so I'm going to flip pages here actually. Okay, so when we do that, I'm going to say that's going to be f1 of t, f2 prime of t, plus g1 of t, g2 prime of t, right? And then I'm going to do the same thing with the other ones, right? Just regrouping f1 prime of t, f2 of t, plus g1 prime of t, g2 of t. Okay. And so then this is really, what is this? Well, that's going to be r of t dotted with what? Well, you've got f2 and g2 derivatives, right? So that's going to be u prime of t. And then what's this over here? Well, this is r prime of t dotted with, now f2 and g2 are unchanged, so that's u of t. Okay. And so that's what we're after, right? Right, the derivative of r of t dotted with u of t is just equal to r of t dotted with u prime of t plus r prime of t dotted with u of t. These are all vectors, of course. It gets a little tiring writing the vector symbol all the time, but you have to, I guess. Okay, so that's that. So that's the simple proof of 4. Now, I would say a lot of them will follow a similar template. Obviously, they won't all involve the dot product and things like that, but really, when you're dealing with vectors like this and this kind of linearity, really what happens over and over is you take the thing you're given, you disassemble it into its components, you rearrange things at the lowest level, and then you kind of reassemble things. And usually the result can kind of fall right out of it. That's sort of the beauty of the linearity of these vectors. So all of this stuff kind of comes out really nicely. Let's do an example. So let's say for let's use some different notation here, see if we can get comfortable with this. For r of t being the vector valued function 1 over t, negative 1, and natural log of t, and u of t, sorry about that, u of t being the function, or the vector valued function t squared negative 2t and then just 1. Okay, we're given these two vector valued functions. Let's find the derivative of the dot product. Okay. So this is pretty much exactly what we just talked about. Okay, so we first need to find r prime of t and u. Well, let's first make sure we know what we're doing here. So d of t of r of t dot u of t is going to be equal to what? It's going to be r of t dot u prime of t plus r prime of t dot u of t. Now, these are all vectors, of course. Got to write that again. Right, so this is what what we're going to apply, but we really are going to need the vector derivatives, the derivatives of r and u. All right, so let's calculate those really quickly first. So r prime of t is going to be equal to, just kind of looking up here, here's r of t, so it's going to be negative 1 over t squared, that's this guy, and then it's going to be 0 and 1 over t. That's r prime. What about u prime? Well, again, just kind of looking at this, it's going to be 2t, negative 2, and 0. Just looking at those three pieces, 2t, negative 2, and 0. Okay, so that means the derivative of the dot product here of these two vector valued functions is just going to be, well, let's write it in here. So we've got r times u prime, r dot u prime, right? So r is 1 over t, negative 1, and natural log of t. And then we're going to dot that against u prime, which is this guy, 2t, negative 2, and 0. And then we're going to add to that this other piece. So we'll have r prime, which is negative 1 over t squared, comma, 0, comma, 1t. And we're going to dot that against u, which was t squared, negative 2t, and 1. Okay, so this maybe looks like total chaos, right? But these are just vectors. Instead of numbers like we're used to, they're functions. Right? So, but this is straightforward. So the dot product here, this first one is going to be, remember this, 1 over t times 2t plus negative 1 times negative 2 plus natural log of t times 0. All right, so we can just write all that out. So it's 1 over t times 2t plus negative 1 times negative 2 plus natural log of t times 0. Right, that's these two, and we have to add to that this one. Same exercise though. The dot product is just component-wise multiplication. It's basically a sum product of the components. All right, so this would be negative 1 over t squared times t squared plus 0. I should really put everything in parentheses just to make sure. Plus 0 times negative 2t plus 1 over t times 1. And now obviously this cleans up a ton. Right? This one in up here, for example, that's 2. This is also 2. This is 0. This is negative 1. That's a 0. And this is a 1 over t. So what do I have here? I've got 2 plus 2 minus 1. So I've got 3 plus 1 over t. That's the derivative of the dot products here. All right, now notice that when you're dealing with strictly with vectors, the dot product is a scalar. But when you're dealing with vector valued functions, the derivative of the dot product here is a, well, dot product of vector valued functions is a real valued function, and in this case, obviously, the derivative of a real valued function is a real valued function, right? So the dot product of vector valued functions is a real valued function. It's like you sort of step down a domain from a vector valued function to a real valued function. And that mirrors what you get with regular vectors, right? With a regular vector, when you take the dot product, it moves down into the scalar world, right? And so it's the same thing here, except you have a real valued function instead of a scalar as the end product. All right, excellent. So that's kind of an intro to the mechanics of differentiation. Now let's talk about integration. So let's move over to integration next. So integration is going to be very similar. All right, so let's start with the definition. Okay, this will be the definition of indefinite and definite integrals over vector valued functions. So if r of t is equal to f of t times I plus g of t times j, right? And I'm just going to take, for the definition, I'm going to use a two-dimensional vector. It works the same with three-dimensional vectors. You see it'll just be adding another layer to the calculation, but it's very straightforward and intuitive, right? Just in the interest of brevity, we'll roll with the 2D definition. Right, so if you've got a two-dimensional vector valued function where f and g are continuous on a b closed interval, then we'll start with the indefinite integral. The indefinite integral of r is given by, okay, the indefinite integral is given by, now it's just the integral of r of t dt, right? And very similar to the derivative, it's a component-wise calculation, right? So you'd say the integral of f of t dt times I plus the integral of g of t dt times j, right? So that's how it works. You just are integrating separately these two real valued functions, and again preserving the structure of the vector valued function, right? And we'll say and the definite integral over a less than or equal to t less than or equal to b is, so you've got the integral from a to b of r of t dt is equal to, now it's similar, it's just got the bounds on there, f of t dt times I plus the integral from a to b of g of t dt times j. Okay. Right, and then again, the 3D version of this is very similar. It's just going to deal with you'll just have a k component, right? So otherwise, the same thing. Now, what happens with the constants of integration? Right, because there'll be constants here. Right, if you're dealing with a two-dimensional vector, you should have two constants of integration. Right, these two pieces right here. If it's a 3D vector, you're going to have three constants. So how do we think about this? Well, here's what you want to think about, right? So this obviously applies just to the indefinite integrals. But basically, when you integrate this, you'll have some antiderivative ft plus c1 times the I vector, plus some other derivative, gt, plus c2 times the j vector. And I'm going to put the third one on here just because I don't want to neglect that. Right? Plus some antiderivative for h times the k vector. Okay, and so you can see what's going to happen here. You can reassemble these right? And you'll have f of t I plus g of t j plus h of t k, right? Plus your constants, right? Your c1 I plus c2j plus c3k. Right, another way to write this, which I think can be kind of help you to see the structure here a little bit, is to write it in the component form like this. Right, so you're basically going to have a vector with all of the antiderivatives in it, and then you'll just have this constant vector. Right, so this could be, you could write it like this. And that's probably how you do want to write it. You just want to kind of write it as plus the c vector. Okay, now obviously RT is an antiderivative here, right? So, okay. All right, so that's not too bad, right? That makes sense. So what's the kind of takeaway here? Well, the takeaway is that integration follows directly from differentiation, right? Just like when we learned about antiderivatives at first, is based on how differentiation worked. And here for vector valued functions, the same story. Let's take a look at a few examples. Okay. So let's integrate the integral of 3t times the I vector plus 3 times the j vector. Right, so start kind of simple here. Well, so this is just 3ti plus 3j. Right, and so what happens here? Well, we integrate each of these pieces separately. Let's write it. So you would do something like this. You would say it's the integral of 3t dt times I plus the integral of 3 dt times j. Okay, and so this would be 3t squared over 2 times the I vector plus this would be 3t times the j vector, and then of course you're going to have the c vector on the end there. All right. Very good. How about, let's try this one. Let's do a definite integral, and let's make it look a little different than we're normally used to. So we say 0 to 1, and now instead of actually writing in ijk, let's actually write it in component form here. So this would be the cubed root of t 1 over t plus 1 and e to the negative t. We want to integrate this vector valued function with respect to t. Okay, so this would be like the integral of r of t dt, right? But here we're going from 0 to 1. Okay, so you would integrate each of the pieces, each of the components. So the integral from 0 to 1 of t to the 1/3 dt, and it's also the integral, and then the second component is the integral of from 0 to 1 of 1 over t plus 1 dt, and then it's the integral from 0 to 1 of e to the negative t dt. Okay, this is a little bit different way to look at it. Sometimes I find that dealing with vector valued functions using this component form just is more straightforward. It's not true for everybody, obviously, but for me, I tend to kind of like it. So what is this integral here? This will be 3/4 times t to the 4/3, right? You're going to add 1 to that. So it would be 3/4 t to the 4/3. Now I have to evaluate that from 0 to 1. This one here, this one is straightforward. This is just the natural log of t plus 1 from 0 up to 1. And then this will just be negative e to the negative t from 0 to 1. And then we just evaluate this guy, right? So this will be 3/4 times 1 to the 4/3 minus 0, right? That's obviously 0. And then this will be the natural log of 2 minus the natural log of 1. And then this will be negative e to the negative 1 minus negative e to the 0. Okay. And finally, we can clean this up. So this will be just 3/4, right? Actually, sorry. This will be 3/4 up front. This will be the natural log of 2 minus natural log of 1, so that'll just be the natural log of 2. And then this is kind of like, what is this? This is negative 1 over e plus 1. Right? And so probably the best way to write it would be to flip it around. So let's rewrite all of these. So 3/4 NL2, ln2, and 1 minus 1 over e. Right? And of course, you could approximate all of these with decimal numbers if you like, but otherwise you can use this. Okay, very good. And so I think that's where we'll stop for this section. Now, coming up next, right, we will get into an application of vector valued functions, basically velocity and acceleration, a nice application from physics. And then we'll continue on with a couple more applications and get into more of the mechanics of how calculus works in 3D, right? But this is a great place to be, right? Because a lot of the stuff that we've already learned, we now see can be applied conveniently and easily to vector valued functions. So, all right, we'll leave it at that, and we'll see you all in the next one. Take care.